Hello everyone, thank you for joining this session. I'm Alexis Tessier, Product Marketing Manager at LUCID. Today we will discuss high dynamic range imaging for automotive sensing application. We will share the latest technology and best practices for imaging with the IMX490 automotive CMOS sensor. In this session we'll discuss what we consider as automotive sensing, share our view on the latest market trends, and highlight the challenges one faces when trying to image automotive application. We'll explain the current technology and what the IMX490 dual pixel HDR technology is bringing. And then what LUCID has built around this sensor, the Triton 054S and its 24-bit pixel pipeline. Finally, we will discuss post-processing and tone mapping strategy to get the most out of this 24-bit output. To begin with a few words about LUCID Vision Labs. LUCID is a Canadian company with 5 main camera family, all based on the Ethernet technology, covering from 1 gigabit, 5 gigabit, and 10 gigabit, both 2D cameras and 3D time-of-flight cameras. All products are designed and manufactured in Canada, and LUCID has a global footprint with its head office in the Vancouver area and satellite office in Germany, China, Japan, and Taiwan. So what do we consider as automotive sensing? All the technology that are used to enable automation of a moving vehicle platform in an open environment. These cover more than standard passenger cars. Those could be car, trucks, robotaxi, but also eventually an autonomous forklift or any kind of autonomous vehicle that needs to move and work in an open environment. Different levels of automations are considered depending on the sensor capabilities and onboard analytics, and these operations should be available day and night, outdoor, in all weather conditions. Those are the different automation levels as defined by the SAE, the Society of Automotive Engineers. Level 0 is no automation, no autonomy. The driver performs the full driving task. Level 1 is driver assistance, where most current vehicles are today. The vehicle control is controlled by the driver, but some features are automated, for instance, lane centering or adaptive cruise control. Level 2 is partial automation. It combines several automated functions, like, for instance, acceleration and steering, but the driver should remain engaged. Lane centering and adaptive cruise control fall into this category. Starting from level 3, we start to be where the vehicle can drive itself under limited conditions, and only if all conditions are met. For instance, the traffic jam pilots feature, where the car will autonomously start and stop in a traffic jam. However, the driver must at all times remain focused on the road and ready to take over if needed. Starting from level 4, we reach high automation capabilities and a vehicle that is capable of performing all driving functions under certain conditions, for instance, in a defined area or geofence area. Human override is optional in this case. Those could be a local driverless taxi, for instance. And level 5 is full automation, where the vehicle performs all the driving tasks and no human interaction or takeover is needed at any time. There are various sub-levels depending on the technology and the definition, but most cars today fall between level 1 and level 2+. Looking at the market trend in the automotive industry, the big buzzword is CASE: connectivity, autonomy, sharing, and electrifications. Those have impact both on the sensing, but also on the how one will use a car or an automotive vehicle. This autonomy is enabled by cameras and sensors, but those sensors, or at least the metadata they produce, can be shared and connected to other vehicles. And this makes the demand on the camera a bit more complex than just simply driving the vehicle. And when we look at this sharing and connectivity, more and more there are analysts that consider that the first autonomous vehicle will not be personal car. There will be robotaxi or delivery truck or some kind of shared vehicle. On the lower left-hand side, we have a recent publication by Yole Development that look at the number of cameras per vehicle. We are currently in 2021 at, in average, 2.4 cameras per car, with the higher-end model having twice as much. The expectation is that the number of cameras will explode to realize the full function, the full safety bubble around the car. However, this transition is a bit slower than initially advertised. On the right-hand side, there's a recent McKinsey survey asking several executives in a company making software, hardware, and services for autonomous vehicles, and their expectation for when the first level 4 and level 5 capability will become available worldwide. Looking at the different sensor technology, camera is one of the sensor technology that is used for making autonomous vehicle. The other two main sensors, optical sensor or position sensor, radar and LiDAR. Both have pros and cons depending on the task. And for object detection, radar and LiDAR will be better than camera because of their range, because of their all-weather capabilities and their faster scanning. However, when we look at object classification, contextualization, or detecting the edge of the object with precision, or looking at visual cues like lane tracking or road signals, camera is most useful. The bad weather and visibility range favors the radar and LiDAR. However, cost and production readiness is definitely the advantage of camera. And more, the trend is to use sensor fusion and to combine those camera outputs, those various sensors together to realize the full function with the highest reliability and performances. Specifically for cameras, those are the four main applications for camera in an autonomous car as of today, autonomous or partially autonomous. The rear view camera, the parking camera, the surround view system that cover all around the car and provide this safety bubble, being aware of the environment at all time. The front sensing camera that is more and more deployed in standard car, used for lane keeping assist and sometimes DVR function or augmented reality function. And more other cameras are deployed, like for instance in the rear view mirror and for sensing various blind spots. However, automotive imaging is a challenge for any camera system. The type and the variety of conditions, illumination, weather condition the camera system has to operate in is very wide. Compared to a typical indoor or factory automation type of system, the camera needs to cope with both sunny, shadow, fog, rain, overcast, day and night, and also indoor, outdoor channels. And also looking at traffic and detecting not only the road and the other car, but also the signal from various car or various traffic lights. And of course, pedestrian. If the vehicle is to be autonomous, it needs to be safe and not create incident with pedestrian or cyclists, for instance. The first issue with the camera system in this condition is the dynamic range. Here we have a chart with the various illuminance of typical condition, from at the top the direct sunlight at zenith on a sunny day, and at the bottom a starry moonless night. These cover a wide range of lux values. And if we look at a typical CMOS sensor with a dynamic range of around 60 dB, this cannot cover all cases. And more the demand for automotive sensing application is to provide 120 dB dynamic range. This requires special sensor technology and special post-processing to realize this. Here we have a quick comparison of a standard CMOS sensor and an automotive sensor in a typical overcast situation. The car drives under a bridge and it's impossible for a standard camera to acquire both good definition of what's under the bridge in the shadow and what's outside. And this could be a safety problem. On the right-hand side, we have the view of this 120 dB automotive sensor output. More problem in today's world, in real world, are LEDs. LEDs are everywhere, and LEDs are not constant like standard incandescent light. They are pulsed. Depending on the combination of the LED frequency and the camera shutter speed, the LED may appear to flicker, or at worst it can appear completely off, completely disabled. This can cause safety issue for detecting a traffic light, detecting an oncoming car, or the car in front of you stopping. And this is further made more complex with more and more city lighting and buildings and signs using also this technology. Here we see a simple example of a recent car on the left-hand side with a standard camera, and its backlight, its rear lights are flickering. On the right-hand side, we see an automotive camera sensor using longer exposure time, providing good image resolution with no LED flickering. So, how it's done with conventional technology to realize those wide dynamic range requirements. The traditional way is to acquire several images at different exposure time to both capture accurately the highlights and the shadowy part of the image, the low light of the image. As the output, several images are acquired, and they can be combined in a single high bit depth, high dynamic range image. This works for a fixed scene, a standard scene like a landscape. However, once we try to apply this method with moving scene, the gap between the various exposures results in motion artifacts, because the vehicle and the scene has moved between the first image and the last image. When we reconstruct the HDR image, it appears with those typical motion artifacts that are not nice to see, but furthermore, they make any type of computer vision algorithm based on this source data almost impossible. And because those typical CMOS sensors lack in the dynamic range, they need to use multiple exposure time, some of them shorter exposure time. We see the illustration there with a typical LED lighting running at maybe 50 Hertz. And on the left-hand side with 2 milliseconds or even 5 millisecond exposure time, it's at some point on some images, the light appears off. While with using longer exposure time of 10 milliseconds, we see the light appears on constantly. However, using 10 milliseconds imaging, 10 millisecond exposure time at all time with a standard sensor will run quite often in saturation issue. We'll see now how automotive sensor developed by Sony propose to overcome this issue. So for its IMX490 sensor, Sony developed a unique pixel technology where each pixel is actually made of two subpixels, a larger one with high sensitivity and a smaller one with lower sensitivity. In addition to this, both pixels are read out with a high gain and a low gain channel. All are exposed and read out at the same time with a common exposure time. What we get at the output are 4 images with 4 different sensitivity that can be combined for an HDR image in motion with no artifacts. In detail, that's an illustration of this sensor design. We have each pixel comprise 2 subpixels with its own microlenses and deep trench isolation to avoid any possible crosstalk. As opposed to using standard pixel, all of the same size with a filter on top of the low sensitivity pixel, this has the benefit of using the same pixel technology and the same pixel substrate for all pixels. Only the surface area and the visible light sensitive area is smaller. This has the benefit of having very similarly shaped quantum efficiency for both pixel type, which help with accurate color reproduction once we process the HDR imagery. And here's how those various subpixels and the high gain and low gain readout map onto the luminance chart. So the large pixel in high gain will image the darker part of the scene, and the small pixel with the lowest gain will image the highlights accurately. What we get as the output are 4 images that are then combined in a higher bit depth, 24-bit HDR image. And since all those pixels used a fixed exposure time, longer, of around 10 milliseconds exposure time, we can be free of most LED flickering issues. Typical street lights or traffic light will use somewhere between 50 and 100 Hertz driving frequency. The LED on a typical car will be between 200 and 400 Hertz. So having a 10 millisecond exposure time should isolate us for this type of issue. Short summary of the different HDR strategy. The conventional HDR method using sequential exposure scheme with multiple exposure. The pros are it's scalable to any kind of dynamic range. We can virtually extend the dynamic range with just adding more pictures. We have to deal with storage space and bit depth, but it's feasible. The cons are motion artifacts, it's prone to LED flickering, and all the HDR processing has to be done off camera, or off sensor at least. On the other hand, the IMX490 subpixel on sensor HDR with its simultaneous and common exposure time exposure scheme provide on sensor true HDR with 120 dynamic range and LED flicker mitigation. The cons, however, it's not any type of camera can be designed around this sensor. A custom camera ISP fine-tuned for the HDR capability of this sensor has to be designed. That's what LUCID did with its Triton 054 camera. At the heart of this camera, the IMX490 back-illuminated stacked CMOS sensor. It's a wide aspect ratio sensor, 1 on 1.55 inches type, so it's a wide sensor, making it easy to get a wide field of view, and providing up to 5 megapixels at 20.8 frames per second in 8-bit output mode through the 1 gigabit PD interface. It's a rolling shutter CMOS sensor, but it provides both good capabilities and good motion capabilities. For this, we use the Triton camera platform. The Triton is an IP67 camera, dust-proof and water-resistant, with GigaVision and PoE compliance and extended temperature range. And this match the very strong requirements of a typical automotive system in terms of shock, vibration, temperature. And the camera embeds a unique 24-bit camera ISP that is designed to get the most out of this sensor and enable the true 120 dB dynamic range to be acquired with no LED flicker mitigation, while at the same time providing low noise and high sensitivity. A few words about what makes the Triton platform unique. It's what we call the factory tough camera. It's designed for use in industrial environments with shock, vibration, electrical discharge, dust-proof, waterproof, and providing secure connector, secure connection with long length power and data on a single cable. The camera is using a die-cast aluminum case for a strong and lightweight chassis of only 67 grams. So we call it a factory tough camera, but it's definitely fitting most of the requirements of a typical automotive camera. installed on a moving platform. Now looking into the camera ISP, this is the standard Triton camera ISP, the one we use for most other sensor, most other machine vision type of sensor. The sensor provides 12-bit output through the sensor interface, and then pixel correction is applied, gain and white balancing, debayering in camera or out camera, color matrix correction, lookup table, eventually gamma, color space conversion. Then we packed the data and we can transmit it. This will not fit the high bit depth capability of the IMX490. Here's what LUCID developed for the Triton 054. The sensor outputs 4 12-bit channels. Those 4 12-bit channels are combined in the sensor ISP. The sensor has its own stacked ISP for HDR processing as a single 24-bit output. Using this wide bit depth output, custom ISP is designed to provide the same function with gain and white balancing, debayering, in or out camera, color correction, lookup table and gamma, and image transmission. So we managed to get this 24-bit output out of the camera. The question now is how to make full use of this information. We need to look at post-processing strategy. Should the HDR be processed in camera and mapped, tone mapped, and output to an 8-bit image? The pros will be a lower bandwidth. We can transmit only 8-bit per pixel and providing the fastest acquisition frame rate with reduced processing burden on the host side. The issue, however, is that all the lookup table and gamma adjustment and tone map we do is fixed and is defined in advance prior to acquisition. The adjustment for this post-processing is limited, and it's difficult to change it dynamically. At the same time, we need to combine this with changing acquisition parameters like auto exposure, auto gain, auto white balance, and those has impact on the camera configuration and installation. The other strategy is to post-process on the host side. So the full 24-bit output is transmitted, and the tone mapping, which is mapping this high bit depth to a more limited dynamic range display or medium, is done on the host side. The pros are the full flexibility of post-processing. From the source image, we can apply various algorithms and decide which provide the best result. Advanced post-processing are possible, including local and adaptive tone mapping, we will explain in a minute, but those are dynamically changing based on the image contrast. And most camera parameters can be fixed in this case. The cons to this approach is a higher bandwidth and a lower frame rate, and the complexity of developing those algorithms and implementing them on the host side. So what's tone mapping? Tone mapping is a technique used in image processing or computer graphic to map a set of colors or dynamic to another to approximate the appearance of a high dynamic range image in a medium that has a more limited dynamic range. A typical display will not reproduce 120 dB dynamic range. To provide the same visually accustomed image, we need to post-process and modify the contrast curve locally to show the most of the valuable information. There are several ways to do this. From the lowest level, which is just extracting 8-bit chunk of data. From a 24-bit image, we can, in essence, create 3 8-bit images, one for the low sensitivity, one for the medium sensitivity, one for the high sensitivity. The next step is to provide a fixed tone mapping, typically gamma or a more advanced lookup table that is defined in advance and applied to all images, all incoming images. A trade-off and a midpoint has to be defined based on the expected operating condition. The next step is to provide this adaptive tone mapping. So the contrast adjustment is changed dynamically based on the image global contrast. So for each image, the contrast curve are modified slightly to display the information differently and make full use of the available dynamic range. The next step, further refinement, is local tone mapping, where the contrast adjustment is not applied to the whole image at once, but the image is segmented in various regions, and a local contrast is adjusted, and a global smoothing function is used to provide uniform adjustment in the image. And the highest level of tone mapping would be a content-aware tone mapping, which is typically an AI engine that looks at the image content and recognizes the image content and will apply different strategy depending on what the scene is showing. Is it a night scene? Is it an urban scene, a moving scene? These type of things. We will not cover all of those in this talk. There are hundreds of research papers, dozens of different algorithms, and several PhD thesis worth of work there. We will show some examples of what can be done using standard off-the-shelf algorithm with the output from the Triton 054 automotive camera. Here on the right-hand side, we see a linear image, which is what if we display the 24-bit with a linear gamma curve. So we just scale down from 24 to 8 bits. And on the bottom side, what we have with adaptive tone mapping. So an automated algorithm that define the best adjustment for this specific image in this case. So bits extraction, it's a function that's provided by LUCID ArenaView software and Arena SDK. From this high bit depth image, we simply extract 3 8-bit images. All of them have a linear contrast curve applied to each subpixel. This is useful for quickly checking the operation of the camera, or if one were to design its own exposure fusion algorithm, so starting from basically applying the same strategy as if several images were acquired at different times. We still get the benefit of no motion artifact and no flicker, but we start from 3 separate images. We have a knowledge base article on LUCID website explaining how to proceed with this approach. The next step would be to provide a gamma correction. So a gamma is a power law that is applied to each pixel value. It can be, so gamma 1 is a linear. If we use lower gamma, we increase the contrast in the darker region. If we use positive gamma above 1, we compress the blacks and stretches the highlights. We see the effect of this. The benefit of gamma is non-linear adjustment with fine gradation. It will never saturate. It will never create heavy posterization. However, this will impact the color reproduction mostly, and the image may appear more dull or flat. Here we see a quick example with various gamma correction applied to the same image as before. So as we increase the gamma, we can clearly see more of the image content, but we can see that the color reproduction and the overall, let's say, pleasing contrast is decreasing in this case. Looking at the previous sequence, and on the upper left side, the lower gamma, next the linear gamma, and the various gamma adjustment there. So next step in the contrast adjustment, in the fixed contrast adjustment, would be to use a lookup table, which can provide much finer control about the curve adjustment than a standard gamma, and more in some way a polynomial adjustment of the contrast curve. We see those can be used to basically raise or crush the black in some parts and stretch the highlights or compress them in a more flexible way. So the image is more pleasing, it's more punchy, if to use a photographic term in this case. That's with a typical S-curve. This can be used also for clipping some of the information. If there is no information in the lower part or the brightest part, they could simply be clipped, and in a sense, any pixel value above the clipping point will have the same pixel value, will be saturated, and same for the black. It can be used also to flatten the contrast or decrease it in the same way with clipping it. So this can be used as some kind of black level adjustment as well. So in summary, with the option we provide with in-camera processing, those would be fixed tone mapping preset before the acquisition. The gamma correction provides a smooth gradation but tends to affect the color rendition. The lookup table is more flexible. You can make an S-curve typically, and it can increase the contrast in a much more stronger way with good color reproduction, but this can lead to saturation and posterization. Posterization is when basically we do not have enough gray level to show the various steps, and we notice the adjustment visually. Those functions can be used to get an in-camera adjustment with the highest dynamic range. You may need to combine those with auto exposure and auto gain function to really cope with all imaging conditions. Now looking at adaptive tone mapping. So this dynamic color adjustment based on global or local contrast in the image. On the left-hand side, we have the linear view, which is a 24-bit image we map to 8-bit with a linear gamma curve. And on the right-hand side, the automated adjustment that has been decided by this algorithm for this specific image that provide both good detail in the shadowy area without saturating the sky and in the outside of this bridge. We see the histogram for both images here. On the left-hand side, we show the 16-bit histogram. We use Excel to build this, and Excel is not playing very well with 16 million gray value that we have in 24-bit, so we scaled down to 16-bit beforehand. And on the right-hand side, we show the histogram adjustment of the tone map image, 8-bit histogram. A quick before and after of this adaptive tone mapping in various conditions. So the exact contrast adjustment will depend on each image content. There are lots of different algorithms. We do not recommend any specific algorithm at this stage. We're showing what we can achieve with a simple sample source code running OpenCV function. Those are built into OpenCV. Each of those algorithms have their own parameterization, and they all have their, let's say, strong suit and more drawback, depending on the condition. Some of them might be more all-terrain, some of them might be more suited for specific conditions like higher saturation or darker images or nighttime. So there are various options available for adaptive tone mapping. And again, lots of research is being published around this. In summary, the strategy for adaptive tone mapping, it's a dynamic contrast adjustment that will change based on each image, on the current image, global and or local contrast adjustments. Most of them are made to be visually pleasing or visually familiar. They are not made to retain data accuracy. They're made to show the appearance of a high dynamic range in a limited dynamic range medium. So the downstream processing pipeline needs to be fine-tuned for this. We are losing some information when we move from 24-bit to 8-bit. We try to map all the significant information, but the computer vision pipeline that is running based on this tone map output needs to be fine-tuned to match this output. So as an example, if you're using an AI model and your AI model has been trained on, let's say, standard image or non-processed image, and you present it with a tone mapped image, it may not perform as expected. On the other hand, if like many AI systems, they've been trained on, let's say, more standard image, not really high dynamic range image, and you present them with a high bit depth, high dynamic range image, they at best will need much more processing resources, or in most cases, they will maybe not provide good performances. So providing them with a first step of adaptive tone mapping before presenting the input data to the neural network might prove useful in this condition. And now to conclude on this quick comparison of the IMX490 running with adaptive tone mapping versus a standard 5 megapixel global shutter CMOS sensor, the IMX264. So both are using their highest bit depth, 24 bit for the 490, 12 bit for the IMX264. Both are using the same adaptive tone mapping algorithm. We can see in those various conditions, so driving through our local furniture store here, that if you look at the right-hand side, it's fully saturated. And here, the auto exposure algorithm, we were running auto exposure on the IMX264 to give it the most chance to get good results. It's being misled by this typical condition. Looking at typical test case driving in and out of tunnel, we see on the left-hand side the IMX490 provide good color reproduction and contrast all the way through tunnel, while the IMX264 standard global shutter factory automation sensor is either too dark or heavily saturated or not adjusting correctly. A typical street scene driving out of shadow into right into the sun. So we see here that was not a particularly sunny day here in Vancouver. We do what we can. We filmed those earlier this month. But we see in this typical scene where the camera auto exposure algorithm needs to decide to expose for the highlights or what's on the trees in the shadows on the side. And it's difficult to get both reproduced accurately. And here, an illustration of the flicker-less nature of the IMX490 automotive sensor, following this modern car with rear LED lights, or those cars with the daytime running light, many of them LED based, that appears to be flickering on the right-hand side with a standard CMOS sensor, and they all appear fixed on the left-hand side. So that's an example of the performance we can achieve with the IMX490 and simple adaptive tone mapping. Now, how to put together the system? The Triton is the IMX490 at its core, and the Triton are a good starting point, but you need to build the whole system. So the Triton is an IP67 camera. We provide IP67 capable cable and lens tube. Here we see the lens tube ring and the lens tube itself. In between those, standard cement lens can be installed. And looking at the various frame rate that can be achieved by the camera, the fastest frame rate is achieved with 8-bit raw, 8-bit Bayer output. By default, we reserve about 10% of the available bandwidth for packet retransmission. If you were to disable this safety feature, the camera can run up to 23.1 frames per second at full resolution, 5.4 megapixel. Using the highest bit depth, the Bayer 24-bit output, we are constrained by the 1 gigabit interface, and the default frame rate will be 6.9 frames per second. And again, with reducing the throughput reserve for packet resend, we can reach up to 7.7 frames per second. If we use lower vertical depth, lower vertical resolution, downgrading to around 1200 pixel height at 8 bits, and with reducing the link throughput, maybe not all the way to 0%, but something around 3 or 4% reserved, we can reach the full 30.6 frames per second, which is the sensor front-end speed. And if we use 24-bit and binning, which is what we used in the demonstration video we've shown earlier, we have 1440 by 920 output at 30 frames per second with about 2% reserve, and with the full reserve 24.7 frames per second. So that is the option. It's a trade-off to be decided depending on the acquisition and processing strategy. We try to provide the most flexibility to our user and let them decide and use the camera according to their needs. One note on the auto exposure, it's optional. It may not be needed in all configuration, but if you were to enable auto exposure, the area where the auto exposure is calculated needs to be decided appropriately. There is not a single solution for this. This will really depend on the application, the implementation, the operating condition. However, one thing to know is saturation signal. The highlight will usually be on the higher upper half of the image. Depending on the installation on the left-hand side, a typical passenger vehicle, the camera sits lower and there would be in the frame, the part that is comprised of the sky will be larger. And in this case, we'd like to run the automatic exposure calculation on the lower part. If we were talking about a truck or a bus or a taller vehicle, the saturated area, depending again on the camera installation and its vantage points, might be the saturation part might be smaller in this case. In any case, we recommend to avoid going below 10 milliseconds in the lower limit for the auto exposure algorithm to avoid HD flicker in this case. And finally, to put the system together, LUCID has a broad portfolio of accessories, various lenses, lens tube fitting with most lenses, and different types of cables, also interface card or PoE injector and mounting accessories. And to select the right lens, we offer a lens calculator on our website that lets you select the camera, the working distance, the image size, and the desired or the desired focal length. And finally, to control the camera and to leverage all its capability, LUCID provides the Arena SDK with its advanced viewer. It's a comprehensive toolkit, multi-platform support, Windows 7, Windows 10, Linux, Ubuntu, and ARM version, multiple language support, C, C++, .NET, C#, Python, with easy-to-use GUI on Windows system that can visualize both 2D and also 3D. Again, LUCID manufactures the Helios time-of-flight camera series. This will be supported as well with our viewer, and a rich selection of examples for simple camera configuration, streaming, trigger, event acquisition, including also some graphical user interface example. It's performance focused. The driver is optimized for low CPU usage, and if you were to use a third-party software solution, LUCID works with most major software vendors to make sure our cameras are compatible, tested, and validated with those. And just a simple illustration of how this technology can be used for other markets. This high dynamic range capability is also well suited for typical industrial application in welding area or even other application. We discover each week customer having using cameras in the way that we do not initially forecasted. This is one example of such. So the IMX490 sensor in the Triton 054 camera is also well suited for this type of welding monitoring application, trying to identify the welding tip, and we see on the non-HDR footage that is almost impossible, basically impossible, and easy to use, easy to achieve with the IMX490 sensor and the Triton 054 cameras. That's all for today. I hope you found this talk interesting. If you have any question, you can ask them now. or you can reach to our various LUCID offices, our headquarters in Vancouver, Richmond near Vancouver, or our local offices in Europe, Asia, and Japan, China, and Taiwan. Thank you very much.